Down there, life continues. The traffic is awful, stocks go on trading, and Star Trek is still showing.
Hello, grade 9 learners, and welcome to today's Natural Sciences lesson. My name is Sianda Madala, and this lesson is proudly brought to you by the Gauteng Department of Education. So today we are still exploring planet Earth and beyond, and we'll be talking about the birth, life, and the death of stars, of which our subtopic as well is on the birth, life, and the death of stars. So without wasting time, let's quickly look at our lesson objectives. These are the following things we should achieve by the end of this lesson. So when this lesson ends, we should be able to explain that stars exist for a finite period, right? They exist for a finite period of time. Also, we need to be able to explain that stars form inside huge clouds of gas and dust called nebulae and far out in space. Also, we need to be able to explain that these nebulae are pulled together by gravity and slowly collapse as they contract, they heat up. And as well as we need to be able to explain that once the temperature is high enough, a nuclear fusion reaction begins and that changes hydrogen to helium. Also, we need to be able to explain that the nuclear fusion reaction radiates large amounts of energy into space. Then we also need to be able to discuss stars in their main sequence, and as well as we need to be able to explain the death of stars. And all this information is found under the CAPS document on page 83. Now moving on to our pre-knowledge, right? Which are the things that we have covered before, and they all lay a foundation to today's topic. Then in grade 7, we started off by introducing the periodic table of elements, right? We said that we have about 118 known elements or discovered elements so far that are all in the periodic table. Then in grade 8, we talked of atoms. We said that atoms are building blocks of matter, and matter is anything and everything that occupies space and has mass, right? We also talked about the relationship between the Earth and other planets in our solar system, mentioning points like we have 8 planets in our solar system. Then in grade 9, we talked of compounds, right? Which are 2 or more elements that are chemically bonded in a fixed ratio. Now, let's look at our baseline activity. Number 1 says define greenhouse effect. The number 2 says explain how the greenhouse effect occurs, right? So I'm going to give you 4 minutes for this activity, but please remember to send in your answers, your comments, or anything regarding this lesson on our WhatsApp number, which is 079 578 2908. So let's meet again after 4 minutes. Welcome back, grade 9 learners. I hope you had enough time to write down your answers for your baseline activity. Remember, our WhatsApp number is 079 578 2908. Please don't be shy to ask any question, to send in your comments or anything regarding this lesson. Right? So let's look at our answers for today's baseline activity. Number 1 was saying define greenhouse effect. So greenhouse effect is simply a warming effect or a natural warming effect caused by the trapping of energy in the atmosphere. Then number 2, explain how the greenhouse effect occurs. This is how, right? The energy from the sun passes through the atmosphere and warms the surface of the earth. That is point number 1. After that has happened, the warmed earth now radiates the energy back into the atmosphere, right? That is point number 2. Then after that has happened, when the warmed or the energy that is radiated back into the atmosphere reaches the atmosphere reach of what? Greenhouse gases. So these greenhouse gases, they do what? They absorb most of this energy, right? They absorb what? Most of this energy. And without the greenhouse gases, most of the energy would pass out to space and the atmosphere would be much colder, right? So now if you need to copy down the corrections, you can take a quick minute to do so. Then after that, we shall proceed with our lesson. Welcome back again, grade 9s. Now let's move on with our lesson, starting off by highlighting some of the important terms that you're going to come across as we proceed with our lesson. The first one that we have there is star, right? We have star because today we're talking about the birth, the life, and death of stars, right? So we need to understand what a star is. So a star is simply a shiny point in the night sky or a ball of burning gas in the universe. Then we have stellar evolution. And stellar evolution means what? The birth, the life, and death of stars. Then we have what? Gravitational contraction, which is the process whereby a nebula's gravity overcomes its internal pressure, causing a collapse. Then we have nuclear fusion, which is the process in which atoms combine to create larger atoms and massive amounts of energy. Now, moving on to today's main meal. Today we're talking about stars, right? And mainly talking about their birth, their life, and death. But before that, we need to understand what a star is, right? So a star is simply what? A shiny point in the night sky or a ball of burning gas in the universe, right? Sometimes we look up the sky and we see some shiny points like these ones, right? These they represent our stars. And I want you to take note of one thing, right? The stars also, they come in different colors, right? Like this one here, it has a blue and a red star. There's some blue stars, red stars, Some look somehow orange, some look also white, right? But there are different colors of stars, right? So this is what we witness when we look up the sky, right? This is what we witness. We see some shiny points in our night sky, and they are called what? Stars. Are we together? So now, since we know what a star is, right? Let's talk now about what? Stellar evolution, which is now the birth, the life, and death of stars, right? So just to simply mention stellar evolution, it means what? The birth and life and death of stars. So stars exist for a finite period of time. What do I mean by that? We mean that stars do not live forever, right? Stars, they are born, they live, and they die, right? Such as other living organisms in our Earth. Are we together? So stellar evolution now is the process by which the star undergoes a sequence of radical changes during its lifetime, right? So it is as it is born, it undergoes some certain stages of development, right? Up until it keeps on glowing in its main sequence, shining, and until it dies, right? This is what we're going to talk about today. Stellar evolution, the process by which a star undergoes these what? Radical changes during its lifetime. Are we together? So now, depending on the mass of the star, this lifetime ranges from 1,000,000 years for the longest stars to a trillions of years for the smallest of stars. Are we together? So now, in this case, it brings us to a nebula. What is a nebula, right? So a nebula now is where the development or the birth of a star begins, right? So it is defined as a thinly spread cloud of interstellar gas and dust, right? A nebula is simply what? A thinly spread cloud of interstellar gas and dust, right? So some nebulae now, they are the remains of a supernova explosion. So meaning what? When a star undergoes what? A supernova explosion, when it blows up, there are some remains that are going to form other stars, right? So a supernova is simply the colossal explosion of a star, right? Looking at this example here, we can see what? The star exploding, right? Into a supernova explosion, right? So meaning what now? Some nebulae or some stars are going to be born from the remains of the star that has undergone what? Supernova explosion. Are we together? So the death and collapse of a massive star can cause this supernova explosion, right? So this means that nebulae can be the remains of old and dead stars, right? As we said, that stars, they come from this interstellar gas and dust, right? Which is a nebula. And a nebula also arises from a supernova explosion of a star, right? So hence what? We say that stars, they are born, they live and they die, and as they die, they leave remains for other stars to be born. Are we together? So most nebulae are gravity-induced condensations of gases where protostars are born, right? So we have a new term here, protostars, right? So protostar now it's what? A development of, or it's a development stage of a star that we're going to talk about. For now, let's look at this NASA image of a nebula, right? As you can see, it is all what? Interstellar gas and dust, right? This is where stars arise. This is where stars are born. So now, without talking too much again, let's look at activity 1 and try to test ourselves, right? Number 1 says, explain what stellar evolution is and why it is a finite process. Number 2, write down the definitions of the following terms: star, stellar formation, and nebula, right? So I'm going to give you 5 minutes for this activity. Then after that, we are going to mark our work. Welcome back again, grade 9s. Now we are going to look at the solutions. Number 1 was saying explain what stellar evolution is and why it is a finite process. Number 2, write down the definition for the following terms: A, star; B, stellar formation; and C, nebula, right? So the answer for number 1, it is what? Stellar evolution is the birth, life, and death of stars, right? So it is a finite process because what? It is the process whereby a star will undergo a sequence of radical changes during its lifetime, and depending on the mass of the star, this lifetime ranges from a few millions for the largest stars to trillions of years for the smallest stars, right? So stars need fuel for stellar evolution, but they only have a limited amount, so they will run out, right? That's why it is a finite process altogether. So because our number 1 is quite long, let me give you a quick minute to copy down the corrections for number 1 before we move on to number 2. Right. Now let's move on to number 2, right? Number 2, you simply had to give the definitions of those words, right? So the first one being star. This is a massive luminous sphere of plasma held together by gravity far out in space, right? Or you can say a ball of burning gas in the universe, right? Also, we have what? Stellar formation. And stellar formation is the process whereby dense regions within molecular clouds of interstellar space, known as nebula, collapse into spheres of plasma to form stars. Then we have nebula, which is a giant interstellar cloud of gas and dust. So the fuels or gases of a nebula are mostly hydrogen and helium, as well as smaller amounts of carbon, nitrogen, and oxygen, right? So our focus is on what? Giant interstellar cloud of gas and dust. So let me give you the last minute to copy down now number 2. Then after that, we proceed with our lesson. Welcome back again, grade 9s. We are still waiting for those answers, questions, or any comments regarding this lesson on our WhatsApp number, which is 079-578-2908. So now let's talk about gravity and contraction, right? So we understand now how a star is formed, right? So part of the nebula now starts to shrink and collapse under the pull of its own gravity, forming a protostar, right? This is the next developmental stage of a star, right? So we said that stars are born from stars. So meaning once one dies out due to a supernova explosion, there's going to be some formation of nebulae, right? So part of the nebulae now will start to shrink and collapse under the pull of their own weight, right? Then form what we know as protostars, right? A protostar, now you can see now it's starting to take what? A shape, right? Starting to take some form of shape. Are we together? So as the protostar now begins to take shape during its gravitational contraction, it heats up, right? It heats up. Are we together? So its gravitational potential energy now, when it heats up, it is now converted to kinetic energy of individual what? Gas particles falling inward, right? So the energy now, as it heats up, it is converted to kinetic energy. There's starting to be some movement, right? The gas particles are falling inward and causing a lot of movement, as we can see also from our picture alongside here. Are we together? So now these particles now, as they are moving, they are bumping into one another and they crash into one another, right? By doing that, they convert this kinetic energy now into heat energy or into thermal energy, right? As there's more and more bumping of each other from these gas particles, the kinetic energy now is transferred to thermal energy, right? So this is how it happens, right? There's a lot of bumping or crashing into one another by these gas particles, right? As you can see, they are in motion. So their motion now, or their kinetic energy, is now converted into thermal energy, right? As it heats up now, the temperature will continue to rise until nuclear fusion begins to take place in the process, right? So nuclear fusion now, it changes what? Hydrogen to helium. Nuclear fusion is the one that keeps the stars going, that keeps the star in its main sequence, or that keeps the star alive, right? So in order for nuclear fusion to take place, there must be tremendous amounts of pressure and heat, right? So more and more bumping of these gas particles is required so that the nuclear fusion is allowed efficiently, right? So this pressure crushes the elements together to create larger elements and more energy. And the element that begins fusing first is hydrogen, right? Because it is the least dense and the easiest to fuse, right? So this is what happens, right? As these gas particles bump into one another, nuclear fusion begins, right? Which is what? The combining of two atoms to form a larger atom, right? You can see now we have two atoms coming together, right? To form now an atom of helium, right? Leaving also what? A neutron as a product on the side that is going to fuse with another atom, and they're going to form more and more larger atoms. Right. So in this case now of nuclear fusion, 4 hydrogen nuclei will fuse together to form one nucleus of helium, right? So the nuclear fusion reaction, it radiates large amounts of energy into space in the form of heat and light, right? As I said, that the nuclear fusion is the one that keeps the star in its main sequence, keeping the star alive and keeping the star going, right? So we have 4 hydrogen nuclei coming together to form what? One nucleus of helium. Are we together? As our picture alongside here illustrates as well. So now, as we said, that nuclear fusion is the one that keeps the stars alive, right? As there's more and more nuclear fusion happening in the cores of stars, it keeps the star lit or in its main sequence. Now, I want us to look at the sun as a star, right? The sun is one of the stars that is on Earth, right? So this one is a medium-sized star, right? It is made up of gases such as hydrogen, helium, carbon, nitrogen, and oxygen. and the sun's energy is able to spread out in the solar system in the form of heat and light. Like now it is during the day, right? We are able to experience the heat and light from the sun, right? So here is the sun as our medium-sized star. So also now inside or in the core of the sun, there's tremendous activity such as nuclear fusion, right? There's nuclear fusion taking place, more and more hydrogen being fused together to form what? Helium. Together. So as we can see now also from our chemical reaction here, we have helium reacting with helium to form, hydrogen reacting with hydrogen to form helium and energy, right? This all happens in the core of the sun. Now looking at the sun here, here is the inner core of the sun, right? If we were to dissect the sun or to cut the sun open, here is our inner core of the sun. Then we have zones such as the radiative zone, we have the convection zone, and also the photosphere, right? Then we have the chromosphere as the outer layer. Right. So other examples of stars, right, just to mention them, they include what? Polaris star, which is this one here that is blue-white in color, right? Then we have what? The Sirius star that is blue in color, right? This is the Sirius star, and as well as we have the Alpha Centauri, right? We have the Alpha Centauri, right? Which is also an example of a star. So now, looking at stars in their main sequence or the main sequence in the life of a star, right? This is when now the star keeps on glowing, more and more nuclear fusion taking place, keeping the star in position and also in light, right? So stars shine because of what? Of the nuclear fusion reaction that is happening what? Deep within the interiors or the cause of stars, right? So as a star forms, the rate of nuclear fusion increases as well, right? Why does it increase now? It increases so that it can maintain what? The main sequence of a star, right? It increases until the amount of energy that is produced from the core is equal to the amount of energy outflowing from the star, right? Or equals to the amount of energy radiating from the surface, right? So nuclear fusion will keep on happening, right? It will increase, right? Until also the amount of energy in the core is equals to the amount that is going out of the star. So this outflow of energy from the core provides the pressure necessary to keep the star from collapsing under its own weight. And as well as the pressure from inside the star will finally equalize the gravity pushing in, and the star will stop contracting, right? So hence we're mentioning also different stars here. I want us to look at the different colors in terms of their meaning, right? Different colors of stars. So usually stars that appear blue in color, they are usually hotter in temperature, right? They are usually hotter, but usually younger when it comes to age, right? They are usually hotter and usually younger than stars that appear red in color, right? So we're talking of the blue colored stars here, such as these ones. These ones, they are usually hotter, but also usually younger than the stars that appear red. So what does it mean about red stars now? It is the complete opposite, right? Stars that appear red, they are less hotter and usually older than the stars that appear blue in color, right? So here is a picture of some red stars. Are we together? And also, however, the larger the mass of the star, the faster it will move through stellar evolution. The larger the star becomes, the faster it will move through its birth, life, and death time, right? So another way of classifying stars is according to their color or spectral class, as this gives an indication of their temperature. So for example, A red dwarf is small and relatively cool star during its main sequence. So I want us to look at this table now to see the effective temperature, the color conventional color description, and the actual apparent color that we see of stars. Right? So now we have what? Kelvin. Right? We have units such as Kelvin to measure our temperatures. Right? So now looking at the effective temperature of what? Of more than 30,000 Kelvin, right? We find a star that is blue in color, right? As we said, that stars that appear blue, they are usually hotter but younger than stars that appear red, right? Then in class B, we find now stars having a temperature of 10,000 to 30,000 Kelvin, right? And they appear deep blue-white in color, right? Now, what's happening here as we move on with our table, we can start to see that the temperatures now of the stars are decreasing, right? From 7,500 to 10,000 Kelvin, we find stars that appear blue-white in color. From 6,000 to 7,500 Kelvin, we find stars that appear white in color. 5,200 to 6,000 Kelvin, we find stars that appear yellowish white in color. But in class K, now we find what? 3,700 to 5,200 Kelvins of temperature, we find stars that are pale yellow orange in color, right? Then along 2,400 to 3,700 Kelvin, we find stars that are light orange in color, right? Then along 1,300 to 2,400 Kelvin, we find stars that are scarlet in color. Then from 500 to 1,300 Kelvin, we find stars that are magenta in color. Then from less than 500, we find stars that are black in color, right? So I want you to look at that statement we talked about, saying that stars that are blue are usually hotter than stars that appear red. And look at the table, right? The red colors, we see them here, right? And the temperature has lowered from there on, right? So now the sun as well as a star in its main sequence, right? In its glowing sequence, meaning it is now, right? Because the sun is still glowing and it hasn't died out, right? So the sun was born like any other star as well, out of a nebulae and as well as into a protostar before it became what it is now, right? So the sun now, it is now in its main sequence and can be classified as a yellow dwarf, right? Due to its temperature as well. And the star now is about 4.57 billion years old, about halfway through its complete life cycle, right? So the life cycle of a star is said to be or meant to be what? 9 billion years. And now we're saying that the star is about what? 4.57 billion years old to date, right? So now to mention the death of stars now, right? There are one of two ways a star can die depending on its size, right? There are one of two ways a star can die depending on its size. And if the star is of low mass, it expands its outer layers. This is how it dies, right? If it is of low mass, it expands its outer layers, creating nebulae, and a white dwarf forms from the core. But if the star is of high mass, death now will occur in a massive explosion known as a supernova, and the remaining core then transforms into a neutron star or a black hole. Now looking at this, right, the death of a red giant, which can die probably because of running out of fuel and contracting, right? So as we said that a star will eventually use up most of its hydrogen and fusion will slow down. The more and more fusion slows down, the more the star glows less, right? The more the star will start to glow less, right? and also it will eventually run out of fuel, right? To run out of fuel and will eventually die. So when that happens now, when the nuclear fusion slows down, right, it stops what? When it stops inside the star, right, it is because there is no longer any outward moving pressure from fusion to counteract the force of gravity, right? Then the star will begin to collapse upon itself. So this is when the star leaves the main sequence now and starts to die. Right. Also, a star can die because of brightening and swelling, right? So when the star runs out of readily available hydrogen, it starts to collapse. Then the nuclear fusion, the fusion of helium begins in the core, now forming carbon and oxygen. So leftover hydrogen gas around the core continues to undergo nuclear fusion and forms an expanding cloud around the core, right? So this cloud is the one that causes the star to swell and form a red giant. And during this whole process now, the red giant can become 1,000 to 10,000 times brighter. So now I want us to look at activity 2, which says explain how a star is born, right? You can use the picture to help you answer the question, and I'm going to give you 5 minutes for this activity. Then after that, we shall mark together. Welcome back, grade 9s. It was saying explain how a star is born, right? So this is the solutions, right? A star is born in a huge cloud of gas and dust known as nebula, right? That is the first point. Also, part of the nebula now begins to shrink under the pull of its own gravity. When that happens, it will form a protostar and the temperature inside continues to rise, right? The protostar will start taking shape, right? As the protostar contracts, pressure and heat build up until nuclear fusion begins to take place at the core, right? Then the nuclear fusion reaction changes hydrogen to helium. So the pressure from inside the star finally equalizes the gravity, pushing in, and the star stops contracting, right? Then lastly, the nuclear fusion reaction radiates large amounts of energy into space and also keeping the star in its main sequence, right? So I'm going to give you a quick minute to copy down the corrections. Then after that, we're going to go to the last part of our lesson. Welcome back again, grade 9s. Now moving on to the last part of our lesson, right? What is a white dwarf now, right? What is a white dwarf, right? So white dwarfs, they form from the core of a dead red giant, right? They form from the core of a dead red giant that were too small to fuse carbon, right? So since they do not undergo fusion, they have no energy source and will gradually fade, right? When they radiate away all of their energy, they will theoretically become a black dwarf, right? Those are white dwarfs. And since white dwarfs cannot be older than the universe, no black dwarfs are currently in existence. So here is a picture of what? A white dwarf. Right. Now, looking at the sun's death as one of the stars, right? So, since the star is smaller, talking in terms of temperature, right? Smaller, it will not explode into a supernova, but instead, it is predicted that it will become a red giant in about 6 billion years, right? So think of the time it has now, right? It has been existing for 4.57 billion years, right? Then in 6 billion years, what will happen? It will become a red giant, right? Where more nuclear fusion will be taking place. More energy in terms of heat will be released from the sun. So meaning what? When this occurs now, all the waters on earth will be vaporized and life will cease to exist, right? So, and also in the final phase, the sun will form a white dwarf and slowly become out of existence. Right. So now let me give you about 3 minutes to ask any questions, to send in those answers or comments in our WhatsApp section, which is 0795782908. Then after that, if there are no or if there is nothing, we are going to wrap up our lesson. Welcome back, grade 9s. Now there is no interaction on our WhatsApp section, so we are going to summarize what we have learned for today. Today we're talking about the birth, life, and death of stars, right? So we said that stars, they exist for a finite period of time, meaning they are born, they live, and they die, right? They do not live forever. And stellar evolution is the process by which a star will undergo a sequence of radical changes during its lifetime, right? So we said that stars are born from stars, and nebulae is that interstellar cloud of gas and dust, right? So a nebula can be defined as a thinly spread cloud of interstellar gas and dust, right? And a nebula is where stars are born as well. And a star is born inside what? A nebula. So part of the nebula begins to shrink under the pull of its own gravity, and this will form what? A protostar, right? Then after that, the temperature inside continues to rise. So as the protostars contract, right, pressure and heat build up until nuclear fusion starts to take place at the core of the star, right? Then the nuclear fusion reaction changes hydrogen to helium in the process. So the pressure from inside the star finally equalizes the gravity pushing in, and the star stops contracting. Then the nuclear fusion reaction radiates large amounts of energy into space, right? So we talked of also there are one of two ways a star can die depending on its size, right? We said that if the star is of low mass, it expands its outer layers, creating nebulae, and a white dwarf forms from the core. But if it is of high mass, death occurs in a massive explosion known as a supernova explosion, and the remaining core then transforms into a neutron star or a black hole. Are we together? So now we also have a homework activity of which I'm going to give you a minute to copy down. Then after that, we are going to say our goodbyes. Welcome back again, grade 9. I hope you have enjoyed today's lesson. Good luck for all your exams, and I hope you do very well, right? From me to you now until we meet again, thank you and goodbye.